So here, when you have the number of equations more than the number of unknowns, so there is a chances that you may have no solutions. You may have solution and you may not have solution. Most of the time, is that we may not have the solution. So here, so if I am representing the same the matrix in terms of the coefficients of x as a into x, being a vector u v and a being a coefficients of u and v, the first column representing your u and the second column representing the v, and that is equals to b. You can check whether it is solvable or not solvable if the vector v can be expressed as the combination of columns of a. Usually this means that we are having a, that is, this is one expression, 0 plus v equals to b1, 5u plus 4v is equals to b2, and 2u plus 4v is equals to b3. If you are representing this in this form, so it's a combination of, it can be expressed as the combination of the columns of v, and then b is in the column space. We call that B is present in the column space if you find the solution. So here take this example, the first example itself. I told you first column represents U, so this is your U, and V, second column represents V, that is V into, I can write the matrix itself as U into first column plus V into second column, and that is the resultant is equals to B. And find the numbers u and v that multiply the first and second columns and gives you the result b. The system is solvable. Attainable right hand side b are all combinations of the columns of a. Okay. So here one possible right hand is the first column u itself. So here one of the solution, if you look at this, if I want to prove this matrix, one of the solution, if I say v equals to 0, what I'll have u equals to 1, that is 1u equals to b1, 5u equals to b2, and 2u equals to b3. That means b1 is equals to 1 and b2 is equals to 5, then u is equals to 1 if I'm taking, and v is equals to 0. This time I'm assigning it to 0, and this if I assign it to 1. What are the values of b1, b2, b3? One of the solutions will be 1, 5, 2. If I reverse the same way, if I take v equals to 1 and u equals to 0, what are the values of b, possible values of b? It will be 0, 4, 4. So this is one of the values. If you solve that, it will be the values of possible right hand sides, that is b1, b2, b3 values will be this one, that is u equals to 1 and v equals to 0, or u equals to 0 and v equals to 1. Third property is the right hand side b equals to 0. If I make b equals to 0, automatically u and v has to be 0, and why we say the solution is, you can obtain the solution. If I make v in this also equals to 0, and that is v equals to 0 and u equals to 0, automatically b will be equals to 0. So that is one more solution, and if I get that also we can call, we have got the solution. So Ax equals to b can be solved if and only if b lies in the plane that is spanned by the two column vectors. This is thin set of attainable p. So I told you if you are finding out that is Ax equals to b can be solved if and only if b lies in the plane and it is spanned by the two columns. It should be spanned by the two columns. The same thing, that is when you solve Ax equals to b, the b should be contained in the columns of A. It should be span in columns A. So that is how you are going to solve Ax equals to b. So here solving Ax equals to b. So when b is equals to 0, we call that space as a null space. So you can see if I call Ax equals to b, and this is itself b is equals to 0, that we call it as a null space of A. Solving this Ax equals to 0, you get a values of x which are tending b equals to 0, and that we call it as a null space of V. And here the null space of a matrix consists of all vectors x such that Ax equals to 0. Same thing I have explained, and it is denoted by n of A. It is a, what will be the subspace? It will be spanning R raised to n, because the number of columns and the number of vectors are n. So all the vectors, n columns itself it will be spanning, and the range of null space of A is R raised to n. So what is the requirements? So it should have the these are the requirements for the null space. If Ax equals to 0 and Ax dash equals to 0, then automatically A of x plus x dash should also be equals to 0. Or you can say Ax equals to 0, Ay equals to 0, then A of Ax plus y also should be equals to 0. So second requirement is that if Ax equals to 0, and if I am multiplying the vector with any other value c and taking and multiplying with the vector A, matrix A, then that polynomial, then also I should get it as 0. So if both, if I don't get these two requirements, if this does not hold good, then I'll not get a solution b equals to 0. B will not be equals to 0. That means what? Ax will not be equals to 0 and it is not a null space. So coming to the problem, you can see this problem as an example. So I have a vector 1, 0. This is one a vector. This is A and this is the vectors u and v. That is, this is your u and this is your v. These are the coefficients of u and v, and let us has to span 0, 0. This is Ax equals to 0. The first equation give, if I solve this, I get the u plus v equals to, that is u plus v equals to 0. So from this what you will get, u equals to 0 you will be getting. And if I, from the second, I will get it as 5 u and the plus 4 v equals to 0. So already you have got what? U equals to 0. So if I substitute, this becomes 0. So from this what happens? V is equals to, that is v is equals to 0. And from the next 2 and 4, it is obvious that 2 and 4 that also will be equals to 0. So here when you solve that, you'll be getting it as 0 vectors. So this is how you are, the first equation gives you 0 and second equation gives you 0, and the null space contains only the vectors 0, 0. Moving on to the next lesson, solving Ax equals to 0 and Ax equals to b. So solving Ax equals to 0 is null space and Ax equals to b is, we call it as a column space, usually the normal solution. This is, we call it as a particular solution. The solution, if I solve Ax equals to b and whatever solution I get, we call it as a particular solution. And this I'll be calling it as a null solution. And the total solution, if I add these two, I'll be getting it as a total solution x. So any vector xn is the null space can be added to a particular solution xp. The solution to all linear equations have this form. So this is the form of solving a matrix. You can have the full total solution is particular solution and null solution. When you want to solve a particular solution, you have to keep b as it is, and when you want to solve a null space, so xn, that time you have to substitute b equals to 0. So that we call it as a complete solution. So axp equals to b. This is a particular solution. This is a null solution, and both together we call it as axp plus xn equals to b, and this we call it as a complete solution. When the column space does not contain every b in R raised to m, so the number of equations, if the b will be spanning R raised to m, the number of equations. So automatically b will be spanning R raised to m. We need these conditions on b that make Ax equals to b solvable. So b should span R raised to m. If b span is less than m, then you cannot have a solution. So here you can see the system one by one.